Hi there, Physics 131. So I wanted to go over homework number 5 from your MyLab and Mastering, because the class average on this was 57%, which is by far the lowest. So this was a difficult homework, and it was quite long as well. So let's start with first question. The first question says, 2 point-like objects are undergoing circular motion at constant speeds. The figure shows 4 possible combinations of paths for the 2 objects, P and Q. Choose which combination is correct for the periods of the objects to be equal. So the period is the amount of time it takes to go around one complete circle. So if their periods of 2 uniform circular motions are equal, it means that they travel through or sweep out equal angles in equal time. So that would be this fourth one. Correct. Part B, choose which combination is correct for the speeds of the objects to be equal. So it looks like P is half the distance away from the center as Q. So the speed of each object is equal to the angular speed, I guess the how far it travels, an angle times the radius. So if it's twice as far out, for the same angular speed, it'll be going twice as fast. So for the same speed, I think this is what we want. We want Q to be going half the angle. So this will be going half of a circumference, which is twice the radius of P. So that's the one I like. Part C, choose which combination is correct for the radial accelerations of the objects to be equal. So remember, the radial acceleration is v squared over r, but we have things in terms of period. The period of Q is either twice the period of P or equal to the period of P. So let's convert that. Remember that v is equal to 2 pi r, the circumference, divided by the period. So v squared is equal to 4 times pi squared times r squared divided by t squared. So the radial acceleration in terms of the period and the radius is 4 pi squared times r squared divided by r times t squared. And then you have the r on the bottom canceling one of the r's on the top. So a sub r is equal to 4 pi squared, some constant, times r divided by t squared. So looking back at what we're asked here, if the r of q is equal to 2 times the r of p, then to compensate, you would need the t of q to be equal to square root of 2 times the t of p. So that when you square it, you've got 2 over 2, and you get the same radial acceleration. So there it looks like 4 times, actually. Q is 4 times, or 2 times. So that doesn't really... Oh, but here's actually one. Here's a situation where the radius of Q is 4 times P, so that'll actually work out. So if the radius of Q is 4 times the radius of P, then TQ is equal to the square root of 4 times the T of P is just twice times the period of P. And so if that's the case, which it is right here, Q goes around half the whole circle in the same amount of time it takes P to go around the full circle, so it's got twice the period. So that's the one I like for C. Correct. Okay. So next question, conceptual question 517. Okay, your friend says that when an object is moving in a circle, there's a force pushing it out away from the center. Why would he say this? Match the words in the left column to the appropriate blank sentences on the right. Make certain each sentence is complete before submitting your answer. When you try to whirl a stone, you feel a force pushing you. I would say you feel a force pulling you out on the rope. But this is a common misconception. If centrifugal force were real, when you let go of the string, the stone would fly off outward. Okay. Instead of it, the stone flies off in the tangential direction. Correct. Okay. Next, conceptual question 5.22. Select examples of situations in which an object moves at a constant speed and has zero acceleration. Ferris wheel ride, that is, no, because that's going in a circle. You walk at a constant speed, so that sounds right. You have to go in a straight line if you're going to have zero acceleration. Car going on a circular track, A box being pushed across the room with applied force canceling the force of friction. Sounds right to me, as long as it's going in a straight line. Part B. Select examples of situations in which an object moves at a constant speed and has a non-zero acceleration. So this is when it's going on a curved path. Ferris wheel, constant rate. Box, no, because that looks like a straight line. Circular track at unchanging speed. It's the other ones. Okay. We're cooking along here. Conceptual question 5.20. Astronauts on the space station orbiting Earth are said to be in zero gravity. Find the gravitational acceleration at the space station that is 350 kilometers above the surface of Earth in terms of g0. The acceleration near the Earth's surface. Assume that the radius of the Earth is 6370 kilometers. So the gravitational acceleration at the space station is I'm going to call that g2, is going to be capital G times the mass of the Earth divided by, I guess, d squared, where d is the distance of space station from the center of the Earth. Okay, and g0 is equal to capital G times the mass of the Earth divided by the radius of the Earth squared. And d is equal to RE plus the height of the space station. Okay, so and g0, as we know, is, well, I guess what we're going to do is just compute g0 is equal to 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 kilograms divided by the radius of the Earth, which is 6370 times 10 to the 3, all squared. I get 9.81 when I do that. If we get d is equal to 6370 plus 350 is equal to 6370 plus 350, 6720 times 10 to the 3 meters, then what we get is, I guess we have to make this G2 is equal to, let's go back to my calculator, it's going to be, let's clear this out, G, which is 6.67 times 10 to the minus 11 times 5.97 times 10 to the power positive 24 divided by, it was 6720 squared. So 6720 times 10 to the 3 squared equals 8.818, it looks like. Okay, so we're trying to find it in terms of G0, so G2 is equal to 8.818 divided by 9.81. Yeah, 0.89, so let's write that in. Make sure I got that. 0.899. Yeah. Okay. G0. So rounding it to two significant figures, you get 0.90. G0. As a multiple of G0 in terms of G0. Well, let's try it as 0.90. Correct. Okay. Part B. What would gravitation acceleration at the space station be if it was 600 kilometers above Earth? Express your answer to two significant figures and include appropriate units. Okay. So this one is if we did 600 kilometers above the surface of the Earth, and so R3 is equal to 370 plus 600, which is equal to 6970. So once again, we'll just go into our calculator here. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 kilograms divided by 6970. So 6970 times 10 to the 3 to get into meters squared equals 8.2 significant, so 8.2 meters per second squared. So I'm going to type 8.2, and the units will be meters divided by seconds to the squared. Submit. Correct. Okay, a mass on a turntable conceptual. A small metal cylinder rests on a circular turntable that is rotating at a constant rate, as illustrated in the diagram, as viewed from above, I guess. Oh, and then there's a bunch of force diagrams. Which of the following set of vectors best describes the velocity, acceleration, and net force acting on the cylinder at the point indicated in the diagram? Oh my goodness. I see. So here we are at, let's put another page here. So the point is right there. Let me write it off to the side perhaps. You've got it here. So it is accelerating. If it's going around like this, rotating at a constant rate. That's weird. It doesn't say if it's rotating clockwise or counterclockwise. I guess all the velocities are to the right. So I'm going to assume that it's clockwise rotation. So that means the velocity is to the right. It means that the acceleration radial is down because it's going at a constant rate. And that means that the net force, the sum of all the forces, is also down. So let's look for that. Where is it here? Yeah, so this should be E. Correct. Part B. Let R be the distance between the cylinder and the center of the turntable. Now assume that the cylinder is moved to a new location, R over 2, from the center of the turntable. Which of the following statements accurately describes the motion of the cylinder at the new location? The speed of the cylinder has decreased. Yes, it will be half of the original speed since it's going around in the same period, but now the radius is smaller, so the circumference is half as small. The speed of the cylinder has increased. The magnitude of the acceleration of the cylinder has decreased. Wait, that's v squared over r. R is less, but v is less. V is half and r is half. So v will go down by, so v squared will go down by a factor of 4, and r will only go down by a factor of 2. So yeah, the acceleration will decrease. The speed and the acceleration of the cylinder have not changed. Let's try that. Okay, good. A ride on the Ferris wheel. A woman rides on a Ferris wheel with a radius of 16 meters that maintains the same speed throughout its motion. To better understand physics, she takes along a digital bathroom scale with memory and sits on it. When she gets off the ride, she uploads the scale readings to a computer and creates a graph of scale reading versus time, figure 1. Note that the graph has a minimum value of 510 newtons and a maximum value of 666 newtons. The acceleration due to gravity is 9.8. What is the woman's mass? Express your answer in kilograms. Well, I think that's what's going to happen as she goes round and round on the Ferris wheel is that, okay, let's look at this. I think what's going to happen, she's going around like this. Let's put it in this direction. At the top, the acceleration is downwards. This is like top. Acceleration is down. And so the top force diagram will have the normal force going up, the m times g going down, and the acceleration going down. And so you will see here, let's call this n top, that the forces, if you set plus r to be down, the sum of the forces in the r direction is going to be mg minus the normal force at the top. Okay, and that's going to be equal to v squared over r times the mass, right? So the normal force at the top, if you rearrange all that stuff, you're going to have, it's going to be, you're going to have to add it to the side minus, so it's going to be mg minus mv squared over r will be the normal force at the top. Hopefully you can rearrange that and get that. And then similarly, the normal force at the bottom is going to be mg plus mv squared over r. And at the sides, the normal force at the side, when the acceleration is towards the center here, then the y components of the acceleration won't be affected, so you'll get the normal force is equal to mg. And so that'll be at the center. This is the, and that's going to be right around 600 newtons. Okay. In fact, I think what it should be is going to be the average of 510 plus 666 divided by 2. So maybe we'll actually do that. 510 plus 666 equals, divided by 2 equals, so 588. And if you want to find her mass, mass is equal to the normal force divided by g. So let's do that. Divided by 9.8 equals 60 kilograms. Let's do 60. Velocity of a roller coaster ranking task. Ooh, fun. 6 roller coaster carts pass over the same semicircular bump, figure 1. The mass m of each cart, including the passenger, and the normal force, lowercase n, of the track on the cart at the top of each bump are given in the figures. Rank the speeds of the different carts as each passes over the top of the bump, largest, smallest. Okay, so so basically it's sort of similar to what was going on before. Here is your velocity v, here is your acceleration down. Define the system as being the cart. So the forces on the system are the upward normal force, the downward mg. We define plus r to be down. The sum of the forces in the r direction is then mg, is positive towards the center of the circle, minus the normal force, which is in the negative r direction, and that's going to be equal to m times v squared over r. So just sort of rearranging that, you've got n, as we did before, is equal to mg minus mv squared over r. But these things are all, they give you the normal force and they give you the mass. And they're asking you about the velocity. Okay, rank the speed. So largest speed, so v squared over r. They're all the same radius. So you're trying to rank the v squared over r. So let's solve for v squared over r. Maybe. So what will we get? We'll get mv squared over r is equal to mg minus the n. Let's divide both sides by m. We get v squared over r is equal to g minus n divided by m. Interesting. So g is a fixed value. So what this means is that and you can find n divided by m for all of these, right? So the larger n divided by m, it's minusing, so the smaller v squared over r, so smaller speed. So all we have to do is rank them opposite for n over m, smaller v squared over r, oops, over r. Right, so 800 divided, so that's 8, so let's put it right here. Can we do it? Yep. So if that's 8, this is 1, so wait, 1 is greater, so 8 is greater than 1, so we want actually this 1 to be up here because we're ranking them in the opposite. Oh wait, no, 8 is greater than 1, so the other way around. We want smallest n over m to largest n over m. So this is 2, which is between 1 and 8. This is 4, which is between 2 and 8. This one's a half, which is less than, oops, wrong. Come on, boy. Trying to get in between there, yeah. So a half is less than 1, and then there's 1, which ranks right like that. Submit. Okay. Curved motion diagram. The motion diagram in the figure represents a pendulum released from rest at an angle of 45 degrees from the vertical. The dots in the motion diagram represent the positions of the pendulum bob at 11 moments separated by equal time intervals. The green arrows represent the average velocity between the adjacent dots. So it speeds up and slows down. Okay, got it? Also given as a compass rose. Okay. What is the direction of the acceleration at the moment 5? Okay, so at moment 5, the velocity is to the right, and I think that's the fastest it's going. So it's speeding up on the way down, it's slowing down on the way up, so it's at the very bottom, it's not changing its speed. So I think that the A will be the acceleration direction straight up towards the center of the circle at the bottom. What is the direction of the acceleration of the object at moments 10 and 0? And they want a comma, 0 and 10, and a comma in between them. So at 0, what I think is going on is that it starts at rest, so it doesn't have any speed. So v squared over r is 0. That means that the radial component of the acceleration is 0. However, it is speeding up in the tangential direction. It's getting faster. So it's going to speed up in the direction d. And then, similarly, at point 10, it'll stop. And so v squared over r, that radial acceleration, will be 0. But it's been slowing down. So it's going to be decelerating. The velocity is up, or was up. It's decelerating, so it is going to be f. Makes sense? Okay. It's a tricky one. Okay, 505. Determine the acceleration of Earth due to its motion around the Sun. Assume the Earth's orbit to be circular with a radius of 1.58 1.5 times 10 to the 8 kilometers. Okay, we can do that. So let's make a blank page here. So acceleration of the Earth is going to be v squared divided by r. The radius, it's going to be circular. The radius r equals 1.5 times 10 to the 8 kilometers. Converting that to meters, we should always do that, is 1.5 times 10 to the 8 plus 3 is 11 meters. Okay, what is the speed of the Earth? That's kind of the question, right? So I think that the speed is going to be 2 pi r, the circumference, divided by the period. And the period is 1 year. We should convert that to SI units, so seconds, right? So we need to convert year to days. So it's going to be 365.25 days. Sorry, it's equal to 1 year. 1 year. So years cancel years. And then we should convert a day to an hour. 24 hours is 1 day. That cancels the days. And then we've got in 1 hour, 3,600 seconds in 1 hour. So hour cancels hours, and then we get the whole thing in seconds. So let's just do that out quickly. So we have it. So 365.25 times 24 times 3,600 is 31 million. So 3.1, say 3.16 times 10 to the 6 times 10 to the 7. So equals 3.16 times 10 to the 7 seconds in 1 year. So we've got a sub r is equal to 4 pi squared. Those r's cancel again. You get r on the top divided by t squared. So it's 4 times 3.14159 squared times 1.5 times 10 to the 11 divided by 3.16 times 10 to the 7 all squared. So let's type that into my calculator. 4 times 3.14159 squared times, times 1.5 times 10 to the 11 divided by, it is 3.16 times 10 to the 7 squared. 3.16 exponent 7 squared equals, ooh, that's pretty small. So it's going to be 0.0059. They say, let's just do it to 2 significant digits because it gives 1.5. So the 596, so 60. So 0060. So it's going to be 0.0060 and meters per second squared. Meters per second. Don't forget to the power 2. Part B. How does this acceleration compare to the acceleration of free fall on Earth? It is much bigger, it's much smaller, much smaller than 9.8. Rolling is a combination of linear and circular motion. In order to study rolling motion, we perform the following experiment. We mark 3 points, A, B, and C, on a bicycle wheel and observe how these points move, while the bicycle is pushed forward 4 centimeters, a distance much smaller than the radius of the wheel. Figure 1. Okay, rolling without slipping. The camera is standing still on the ground. A is the point where the wheel initially is touching the ground. B is the point on the wheel's axis. And C is the point at the top of the wheel, directly above point A. So, okay. Part A. Determine the displacements of points A, B, and C as observed by a stationary observer, and put commas in between them. Answer in centimeters. Okay, so XA, it's rolling without slipping, so that point A should not move, right? So let's put 0. Point B, well, it says right there, it's pushed forward 4 centimeters. So the bike moves 4 centimeters. So point B is attached to the bike. So that's going to be 4 centimeters. And lastly, point C, how far does it move? So, and they suggested using similar triangles. So the similar triangles that they're talking about here are going to be for point B. So if this is point A, and this is point B, at 1 and then it goes to B at 2, that the wheel rotates that certain angle. And then there's a bigger angle, and by the way, this is the radius of the wheel, right? R. And then if you look at point C, it sweeps out that same amount of angle. Oops. I shouldn't say C. So if this is point A, this is point C1, it goes from here to here to C2. This angle and this angle are the same, but here is a larger distance. This is 2R because it's twice the radius of the whole wheel. So what it means is that if this is 4 centimeters, here I gotta be more careful. If this is 4 centimeters, then this will be 8 centimeters. So 8. Part B, using your answers from the previous part, determine the speed of the points A, B, and C with respect to the ground for the bicycle that is moving at a constant speed of 4 meters per second. So we did this a little bit before, but VA will be 0 because it's stationary, rolling without slipping. VB is the same as the speed of the bike, 4 meters per second, and the top point, point C, is moving at twice the speed of the axle, so 8 meters per second. How would the speeds of the points change if the observer were moving in the same direction as the bicycle, but with the same speed as the bicycle? So these are these prime, so you're in the frame where the axle is 0, so VB is 0. In that case, VA is going to be like going backwards actually, so that'll be your negative 4 meters per second. B is stationary because you're moving with the bike and the axle is stationary, and C will be going plus 4 meters per second. How would the speed of the points change if the observer were moving in the same direction as the bicycle but twice as fast as the bicycle? So if you're going twice as fast that way, again, you just take, so what we did actually get from 048 to negative 404 is we just subtracted 4 from all those numbers. 0 minus 4 is minus 4. 4 minus 4 is 0. 8 minus 4 is 0. So if you're going even 4 meters per second faster, you do negative 4 minus 4 is negative 8. 0 minus 4 is negative 4. Negative 4. And 4 minus 4 is 0. So just 0. Okay. Good. Okay, we're getting through it. 11 out of 16. Problem 5.26. A person sitting in a chair, combined mass 80 kilograms, is attached to a 6 meter long cable. The person moves in a horizontal circle. The cable angle theta is 62 degrees below the horizontal. What is the person's speed? Note the radius of the circle is not 6 meters. Ah, yes. Okay, so I get it. Let's move that over there. Okay, so I think the way we're going to do that is something about 62 degrees below the horizontal. 62 degrees equals theta. Here is the person sitting in a chair. The mass here is 80 kilograms. Okay, and this whole distance here is a 6 meter long cable, so I'm going to call this D. D is equal to 6.0 meters. Okay, and so this is the circular path going around in a horizontal circle. So this is your radius right there, R. So we need to find, using geometry, what R is. And I think by the Z rule that this will also be 62 degrees right there. That'll be theta right there. So we can say right now, if we want to find R, if this is D and this is R and this is theta, that the cosine, and here's your right angle, the cosine of theta is equal to R divided by D. So R is equal to D times cosine theta. So that's important. What is the person's speed? Doesn't give you much, eh? So we are trying to find V. So what I think is going on here, we can say that it's accelerating inwards. acceleration in the r direction is equal to v squared divided by r. Okay, and the force diagram is that we've got this force pulling up, the tension of the rope on the person, and we've got this mg, force of the earth or g of the earth on the person. Okay, those are the only forces on this object. The vertical force is balance. We're going to say that we're going to define y to be up, r to be towards the center of the circle, so define like that. And the main thing, I think, is that the sum of the forces in the r direction is going to be equal to the mass times v squared over r. Okay? And that's just going to be equal to the tension in the r component. So once again, what we have to do is, if this is tr and this is ty, this is going to be theta up here, that bigger angle, I think, and this is going to be t. So tr is equal to t times cosine theta. The problem is we don't know the tension. So I think the other thing we need to do is to say that the forces in the y direction equal 0. There's no vertical acceleration. So that's going to be t sub y minus mg. And so that'll be saying that t sub y, which is t times sine theta, is equal to mg. So t is equal to mg divided by sine theta. So we've got a value for t, okay, which we can plug into tr. T cos theta is going to be equal to the mass times v squared over r. So we've got these two equations, and we can plug this equation for t into this equation for the radial velocity. So we can do that. Go down a little bit. We say that mv squared over r is equal to mg divided by sine theta times cosine of theta. M's cancel on both sides. We're solving out for v, right? So let's try to collect all terms. We've got v squared is equal to g times r times cosine theta divided by sine theta. And remember that r was equal to d cos theta. So it's equal to g times d times cos squared theta. There's cos theta times cos theta is cos squared theta divided by sine theta. And we're going to take the square root of both sides. So v is equal to the square root of g times d times cos squared theta divided by sine theta. So it's equal to the square root of 9.8 times 6 times the cosine of 62 squared divided by the sine of 62. And then you square root the whole thing. So want to do that in the calculator? Can we do it? Let's do clear. 9.8 times 6 times, I'm going to do 60, are we in degrees mode? No. Degree. Good. Times 62, where's the cosine button? Cos squared equals, and then divided by 62 sine equals, and then the square root of that whole thing, 3.83 meters per second. And I think that's 3.8 to keep it in two significant digits, meters per second. Okay, problem 12. A car moves around a 50-meter radius highway curve. The road, banked at 10 degrees relative to the horizontal, is wet and icy, so that the coefficient of friction is this is static friction, is approximately 0. At what speed should the car travel so that it makes the turn without slipping? So what this means, this is actually We did this in class 15. So if you look at the class 15 notes in the YouTube video, you'll see what I did there. Here's mu sub s equals 0, and you've got a curve here. This is like the back of the car. I don't know if that's like the tailpipe or something like that. It's going into the page here, and so over here is the plus r direction, and we say I think what we found is that v critical was equal to the square root of g, this is theta, times r times sine theta divided by cosine theta. And so in our case, that's going to be 9.8 times 50 meters times sine of 10 divided by cosine of 10. So let's clear that out. 9.8 times 50 times 10 sine divided by 10 cosine equals, and then square root, 9.295 meters per second. It is asking, let's see, this is, well, might as well do two. These is either 1 or 2 significant digits. Let's do 2, 9.3. 0.3 meters per second. So meters divided by seconds. Submit. Question 13. You have to design a loop-the-loop for a new amusement park so that when each car passes the top of the loop, inverted upside down, each seat exerts a force against the passenger's bottom that has a magnitude equal to 1.5 times the gravitational force that the Earth exerts on the passenger. Will the loop work equally for passengers of any mass? I mean, I would think so, because what you're going to do is set up the acceleration so that this normal force is mg times 1.5, right? So, like that. That's my gut feeling there. Write the equation for the speed of the car at the top of the loop-to-loop for a loop of radius r. Assume the mass of car is m. Express your answer in terms of some or all of the variables. M, r, and appropriate constants like g. Okay, no problem. So let's start a new page here. So where you are is a circular path. You're up here. Here's the cart. And you're going at a speed v. Okay, we're going to find v, which is constant. There's some acceleration a sub r, which is down. So we're going to define plus r to be in the down direction. And we do the force, so system equals, I guess it'll be the passenger. So there's a passenger here, P, mass M, and the radius of the curve here is capital R. Okay, so let's draw the force diagram of the passenger. So first of all, there's going to be the force of the Earth on the passenger. That's the gravity force. And second of all, there's going to be, this would be 1.5 of it, of the normal force of the car on the passenger. Okay, and the acceleration is in the down direction. So, basically, acceleration is equal to v squared over capital R is equal to the sum of all the forces in the r direction. Let's get my eraser. Divided by the mass, right? So that's going to be 1 over the mass times the normal force plus m times g. And what we're going to do is to set the normal force is equal to 1.5 times m times g, right? Because it says Each seat exerts a force against the passenger's bottom that has a magnitude equal to 1.5 times the gravitational force that the Earth exerts in the passenger, which is mg, so 1.5. So you say that v squared over capital R equals 1 over m times 1.5 mg plus mg. I'm just going to solve it out for v. So you get v squared is equal to r divided by m times 1.5 plus 1 is 2.5 times m times g, and then the masses cancel. That's kind of what I thought at the beginning, the masses would cancel, and they did. It's just a guess. So if I'd done this all first, then I would have gotten 2.5. So v is the square root of 2.5 times capital R times g, all square root. So let's type that in here. Get a square root sign of 2.5 capital R G. Submit. Oops, and then there's a part C. Calculate the speed of car on the top of the loop-to-loop for a loop of radius 15 meters. So that's going to be 15 times g times 2.5, so let's do that. It's 2.5 times 9.8 times, what was it again, 15 meters? Yeah, 15 meters. 15 equals square root 19.17. Probably two significant digits there. It's going to be 19. 19 meters divided by seconds. Submit. Okay, we're getting there, folks. We're on question number 14. Okay. It says, if the masses, part A, if the masses of Earth and the Moon were both doubled, by how much would the radius of the Moon's orbit about the Earth have to change if its speed did not change? R prime is the mean distance between Earth and Moon after changing of the mass. EM and REM. So you're trying to find REM prime divided by REM. Okay. Okay, no problem. So what we're going to do, here is Moon, the mass with the mass of the Moon. And down here is Earth with the mass of the Earth. The Moon is going around the Earth in a big circular path with radius REM, without the prime, because this is when they have their normal masses. And the Moon is traveling at a speed v. And so what we're going to do is define this direction to be r, in a plus r direction. The sum of forces in the r direction is equal to the force of gravity of the Earth on the Moon, which is going to be the mass of the Moon times a sub r, right? Because it's the net force. So it's the mass of the Moon times v squared over r. REM, that is. And this equals this g times the mass of the Earth times the mass of the Moon divided by REM squared. That equals m times v squared over REM. So right now what we can do is divide both sides by the mass of the Moon. You can multiply both sides by the radius here, and that gets rid of the squared. Let's redraw this. So you've got g times mass of the Earth divided by radius of the Earth, REM, is equal to v squared. Okay, so that's a good equation to kind of remember here. And now in our case, what's happening is that the speed is staying the same. V is the same, but now you've got 2 times the mass of the Moon, which is orbiting around 2 times the mass of the Earth. Okay, but only the mass of the Earth comes into this. So, and then this distance now is REM prime. So what you have is g, which is the same. you've got times 2 mass of the Earth divided by REM prime. And that actually equals v squared because v was the same. And so I'm just going to plug that into here. So that's actually equal to g times me divided by REM. A times over by REM prime divided by REM. And then you divide by g and divide by mass of the Earth, and you just get 2. The next question is, by how much would its speed have to change if its radius did not change? Assume that v is the speed before changing of the mass, and v prime is the speed after changing the mass. So we're going to use the same equation, v squared, but now the next situation, part B, is a situation where you've got, again, 2m, 2 mass of the moon, going now at v prime, but it's that same distance, REM, from 2 times the mass of the Earth. So what you'll have in this case is g times 2 mass of the Earth, looking at this equation in the square, divided by REM, so that's now the same, is equal to v prime squared. Okay, so we're going to need to solve this one out for what's the same. So it's g times 2me divided by v prime squared is equal to REM. And then that is going to be equal to g times me divided by v squared, by just solving this equation for REM and then setting them equal. So once again, the g's cancel, you're going to get v prime squared divided by v squared is equal to 2. And so v prime divided by v should be square root of 2. I wonder if I'm able to just type that in without actually doing it. So I have a square root sign. 2. Sigma. Yeah. Mastering physics is smart that way. Okay. 15. Suppose that Earth rotated much faster on its axis so that people were almost weightless when at the Earth's surface. That'd be fun. How long would the length of the day be on this new Earth? Assume that RE equals 6.3, write that down over here, 6.37 times 10 to the 6 meters is the radius of the Earth. Okay, great. So what we're going to do is draw a circle. You're going at some speed v, and there's a normal force upwards on you, and there's a mg down, but you want to have normal force equal to 0 for weightless. So once again, this is the plus r direction. You've got a sub r down is equal to v squared over r. We'll call it re, because that's what it was in the problem. So the sum of the forces in the r direction is MAR is equal to m times g, where g is 9.8, I guess. So we can find the velocity. I think what we're going to do is find speed, and then we're going to find length of day is the time for you to go all the way around a circle, for you to travel the circle of circumference 2 times pi times r. This will be 1 day. Okay, so we've sort of done this one before. How fast would you be? It's called a low Earth orbit. So v squared over re is equal to g. So v is equal to the square root of g times r. So now that we have the speed, we know the distance that the thing travels. D is equal to 2 pi times r sub e, and this is a constant speed. So the equation of constant velocity, or constant speed in this case, for a path length, this is like the path length, is just going to be v is equal to the distance divided by the time. We're trying to solve for the time. The time is equal to the distance divided by the speed. So time is equal to 2 pi times r sub e divided by the square root of g times r sub e. Okay, so and there's square root of r sub e here. So one way you can get rid of the 2r sub e's is you go 2 pi divided by, so you can, I guess, divide top and bottom by re, and when that comes into the square root, you get g times re divided by re squared. So you end up with 2 times pi divided by g divided by re. So that's all on the bottom. So just to make it look a little prettier, I've got 2 times pi times the square root of r sub e divided by g. So that's equal to 2 times 3.14159 times the square root of 6.37 times 10 to the 6 meters divided by 9.8 meters per second squared. So can we do that? Why don't we do, let's do the square rooty part first. So it's going to be 6.37 times 10 to the 6 divided by 9.8 equals square root times 2 times 3.14159 equals, ooh, that's a lot of seconds. How could that be right? Maybe we should try that again. I got time I typed something wrong. 6.37 times 10 to the 6 divided by 9.8 equals square root. Maybe I pressed squared. Square root? Yeah, 800. Okay, good. Times 2 times 3.14 equals 5,000. Okay, I like that a little better. 5,063. T equals 5,063 seconds. And it wants it in hours. Okay, good. So we can times it by 60, or divide it, I guess. 60 seconds is 1 minute, and do 1 hour is 60 minutes. So that way you've got seconds cancels seconds, minutes cancels minutes, and you've got the whole thing in hours. So back to our calculator, divided by 60 equals, divided by 60 equals 1.406. 1.406 hours. Okay, that would be the new length of your day. Wow, that's actually not much less than 24 hours. So if we had a 1.4 hour a day, we'd all be floating on the equator. And let's use 3 significant digits, 1.41. And that's also the length of a low Earth orbit, about an hour and a half. Okay, last question. Oh my God, this was a long problem set. I realize I'm giving you guys a lot of work. Okay, Isabel notices that if she places a small plastic box on a horizontal wooden desk and slowly increases the rotational frequency of the disc, the box flies off the disc at a certain rotational frequency. She investigates this phenomenon by placing the box at different distances d from the edge of the disc and measuring the period of the disc revolution, t, when the box flies off the disc. That sounds like a friction experiment. Her data are presented in the table below. Based on these data, Isabel is able to determine the radius of the disc and the coefficient of static friction between wood and plastic. Determine them using her data. Write an expression for the period t in the limiting case when the static friction force is the largest. Okay, so I think we have to work this out. Let's do a blank thing. So this is the top view. What we've got here is a disk of radius r, which we don't know, and we've got the box right there, and this is some distance d from the edge, which is a bit weird, and then the whole thing is going at some speed v, and the period is t. And then this is the rear view, which is that here's the center, here's the box, and you always do your force diagram with the rear view. So system is the box, force diagram. In this case, what's going on is we'll define R to be towards the inside of the circle and Y to be up. Okay, define. So what you've got is the static friction force of the disc on the box. You've got the normal force of the disc on the box, and you've got the gravity force. Whoops. The force of gravity of the Earth on the box. And I think those are the only forces, and the whole thing is accelerating. A sub r is equal to v squared over r. No, wait a second. Not right. A sub r is equal to v squared divided by this distance, which is going to be, call that a or something, a, where a plus d is equal to r. Let's not forget that. Okay. Wait, express your answer in terms of the disk radius rd, the distance from the edge d. So I should have been calling this thing r capital D. So r capital D. Okay, so that's still a. You guys following? So, and what we're going to do is we're going to assume, it says it's a limit here, so Fs equals Fs max, which is going to be mu sub s times the normal force. And so what we've got is the sum of the forces in the y direction equals 0. That's equal to normal force minus m times g. So what that means is the normal force equals mg, as it often does in these problems. And then the sum of the forces in the r direction is equal to the mass of the object times v squared over a in this case, the a sub r. That's going to be equal to just the mu sub s times m times g. It's just the static friction force, which is the maximum. And the m's cancel. So what are we trying to do here? We're trying to find the period. Okay, so v squared divided by, let's solve out for a. A is r sub d minus d, minus capital D, is equal to mu sub s times g. And then the other thing that we know is that the speed is equal to the distance, the circumference, 2 pi times, I guess, this a, divided by the period. Okay, so the period is equal to 2 pi, well, we can actually, let's just take this and sub it into there, and then we'll solve out for period. So I've got 2 times pi times r d minus lowercase d divided by t, all squared, times 1 over r minus rd is equal to mu sub s times g. So there's a lot of stupid algebra going on here, but you can do this. We're going to square all this stuff. This thingy is going to cancel this squared up here, one of the, I guess, the squares there, but you're still going to have a bunch of squares. You're going to have 4 times pi squared divided by t squared, but then there's just going to be r d minus d, because that was squared, but then it canceled with one of those r minus d, is equal to mu sub s times g. We're going to solve for period. So let's get all the periods on one side of the equation. You've got 4 pi squared divided by mu sub s times g times r d minus d is equal to t squared. So t is equal to the square root of, maybe I can get some of this out of here. The 4 pi squareds can come out. So let's erase that again. you're going to have a 2 pi times the square root of r d minus d divided by mu sub s times g. So that's the distance divided by meters per second squared. So that's going to be a second squared square root. You're going to get seconds. So the units are seconds, so that should be okay. We just have to type this in here. So it's 2 times pi. Let's get our little pi here. Times the square root of some big fraction. And let's open up a bracket here. Bracket r d minus d, so r sub d minus d, close bracket, divided by mu sub s times g. So that's going to be, find mu, put a subscript of s, and then times it by g. Okay, likes it. Part B, rearrange your equation to obtain a linear dependence on d and draw a graph to determine unknown quantities. So all that means is that we're taking this equation for the period and we're trying to make it into some linear function of d, like y equals mx plus b. So the d is the x and the t is the y. So the first step is going to be actually, you have to square both sides to get the d linear. So, and that's actually indicated here. If you look at this graph, they've done t squared versus d. So that's what we're trying to look for here. So if we do t squared is equal to 4 times pi squared times, now this square root just becomes r d minus d over mu sub s g. Let's multiply through by the 4 pi squared and separate this all out. So you've got 4 times pi squared times r sub d divided by mu sub s times g minus 4 times pi squared times d divided by mu sub s times g. So if we want to rearrange that into the y equals mx plus b format, you've got t squared is equal to negative 4 pi squared over mu sub s times g times d, where d is the distance from the edge of the disk, plus 4 pi squared times the radius of the disk divided by mu sub s times g. So we've got the format here is y equals mx plus b, where y is t squared, x is equal to this distance d, the slope m is equal to negative 4 pi squared over mu sub s times g. So the only thing we don't know in the slope is the coefficient of static friction, and the y-intercept, right down a little bit, is b is equal to 4 pi squared times the radius of the disk divided by mu sub s times g. So if we already know mu sub s from the slope, we can find the radius of the disk from the y-intercept. So it's good to have that equation now. Y equals mx plus b, where the y is the t squared and the d is the x coordinate. That's what we're going to graph here. But in fact, in this part b, all they're asking you to do is to just add the points of the graph. So we're graphing t squared versus d, so let's actually make a little table so that we have it of t squared, whoop, and versus d. So, and d is going to increase. So I'm going to actually just draw 0.13, 0.14, 0.15, 0.16, and 0.17. The t squared values are going to be 0.55 squared is 0.302. That's your 0.303. Just working up the chart there, 0.65 squared is 0.423. 0.72 squared is 0.518. 0.8 squared is 0.64. And lastly, 0.85 squared is 0.723. So what we can do now is take these numbers and just stick them on this graph, and then we'll have a little plot. So we'll do plus with the t-squared values. It allows you to draw these little dots. So the first one, 0.13, goes up to 0.72, and then 0.14 is 0.64, 0.15 is 0.52, 0.16 is 0.42, and 0.17 is 0.3. And just make sure these are right. 7.2, 6.4, or 0.64, 0.52, 0.42, and 0.30. Okay. So it's just a downward sloping graph, and it looks pretty linear. Okay. Part C is determine the coefficient of static friction between the wood and the plastic. Okay, so from that you need the slope of this. So the slope, which we called m, is equal to the rise over the run. So if we're looking at this table, we're actually looking at the rise of t squared divided by the run of d, right? So that's going to be 0.85 squared minus 0.55 squared divided by 0.13 minus 0.17. So 0.85 squared minus 0.55 squared, 0.85 squared minus 0.55 squared equals 0.42. That's the rise divided by the run, which is negative 0.13 minus 0.17. It's going to be negative 0.04. So 0.42 divided by 0.04 negative is equal to negative 10.5. That's the slope of this curve, and from this equation right here we can solve for mu sub s is equal to negative 4 pi squared divided by that slope times g. So it's going to be negative 4 times pi, 3.14159 squared, divided by negative 10.5 times 9.8. Okay, so the negatives can cancel there. I'll just make these pluses. And I'm going to get 4 times 3.14159 squared divided by 10.5 equals divided by 9.8 equals. And I got 0.3837. That's good. So let's put between wood and plastic 0. Let's do it in 2 significant digits. 0.38. So didn't like my graph for whatever reason, not sure why, but I did like my part C. And then the radius of the disk. So now that we know that, and we know mu sub s, we can look for whatever the y-intercept of this is. So I would say that certainly, if you're still watching this, I'm impressed. This whole problem is not for the faint of heart. So the way you're going to find the y-intercept is to look at a particular point, right? So if we've got a y is equal to mx plus b, this means that if you have a value of y and a value of x, then the value of b is going to be y minus m times x. So what we can do here is we can say, let's just take this first one. So let's do t squared. So y is t squared, right? So 0.55 squared minus your m, which is negative 10.5, we found that from before, times your x, which was d, which is 0.17. So it's going to be 0.55 squared plus 10.5 times 0.17. And that'll be your value of b. Let's just work that out. 10.5 times 0.17 equals plus 0.55 squared equals. So it's 2.088. That's the y-intercept. And then we had this whole thing up here that b is 4 pi squared times rd divided by, so it's going to be that rd is equal to, we just have to rearrange all this stuff for rd. So it's going to be b times mu sub s times g divided by 4 pi squared. So hang in there, folks. We are almost done this problem. So it's going to be 2.088 times the mu sub s, we found that before, 0.3837 times 9.8, all divided by 4 times pi squared. I noticed that I had a pi in my calculator there, so maybe I can do that. But let's just pull this over here, so don't forget everything. And we're going to have, clear this out, 2.088 times 0.3837 times 9.8 divided by 4 equals divided by pi squared equals. And I get 0.1 1988, 1989. So 0.1989. That is going to be in meters, is the radius of the disk. So, and it's got meters, yeah, so and let's do it in 2 significant digits, so it'll be 0.20 meters.